Let's solve problem 6.29 for Microelectronic Circuits 8th edition by Sedra and Smith. There are three circuits with different measurements made on them, and we need to find the value of beta for each transistor. So how can we do that? For this problem, we're going to be leveraging the equation beta equals collector current divided by base current. Now we can see we have a NPN transistor, which means the emitter is the top, the base is the middle, and the collector is the bottom. Now let's discuss the EBJ and CBJ and figure out which mode of operation the transistor is in. So EBJ goes from base to emitter, which is 4.3 volts to 5 volts, low to high, so the EBJ is reverse biased. The CBJ goes from base to collector, so 4.3 to 2, high to low, so the CBJ is forward biased, and this NPN transistor is operating in the active region. So therefore we can leverage this equation, beta equals collector current divided by base current. So let's start by solving for the collector current. That is going to be 2 volts minus 0 volts because it's grounded, divided by 2 kilo ohms, which is equal to 1 milliamp. Then our base current will be 4.3 volts minus 0 divided by 200 kilo ohms. So that's going to be 0.0215 milliamps. So beta is equal to 1 milliamp divided by 0.0215 milliamps. That's equal to 46.5, which is a pretty reasonable number for beta. So let's move on to the next circuit. Okay, let's solve circuit B. So again, we have an NPN transistor. So we have the emitter here, base here, and the collector. I'm not going to go through the voltages again, but again, this transistor is operating in active region, which means beta will be equal to collector current divided by base current. Now we need to be a little careful with this figure because of this wire. So this wire is still the base current, but it's connected to this node with the collector. So what does this mean? Before entering the node, be the collector current, and because the base is now connected to the collector, this current would be the base current plus the collector current. So let's solve for base current first. That's going to be 4.3 minus 3 divided by 27 kilo ohms, which is equal to 0.048 milliamps. Now I don't know what my collector current is yet, but I can solve for the summation to be 3 minus 0 divided by 750 ohms. That is equal to 4 milliamps. So now I can calculate my collector current to be this 4 milliamps minus the base current. So my collector current is 3.952 milliamps. Now we can properly calculate beta to be collector current divided by base current, or 3.952 divided by 0.048, which is equal to 82.3. So that is our value of beta for this problem. Let's continue. All right, let's solve the final circuit. This is a pretty similar setup to the last circuit, except I'm missing my voltage here, my collector voltage. This is still emitter, base, and collector. This one I'm getting my emitter voltage, so I can solve for my emitter current. 10 minus 7 divided by 1 kilo ohms is equal to 3 milliamps. So how can I solve for this collector voltage because I really need that. Well, again, this wire will be base voltage. This wire will be collector voltage. And because of that, this wire will be base plus collector. But we also know that emitter current is just equal to base plus collector. So that means this wire is 3 milliamps, which means VC is equal to 0 volts plus the emitter current multiplied by 1.5 kilo ohms, which is equal to 4.5 volts. Sorry, I can't write. 4.5 volts. Okay. That means I can calculate base voltage to be 6.3 volts minus 4.5 volts divided by 45 kilo ohms, which is equal to 0.04 milliamps. And finally, I can calculate collector current to be IE minus IB. So IC is equal to 3 milliamps minus 0.04 milliamps. So collector current is equal to 2.96 milliamps, and therefore beta is equal to 2.96 divided by 0.04, which is equal to 74. And that solves the problem. Thank you for watching my video. For any comments, questions, or video suggestions, please contact me in the comment section or by my email. Thank you, and have a nice day.